Thank you, Tom. And thank you everyone for joining us for the webinar series, Decoding Defects, Failure Analysis using X-ray CT. Today is the second episode of this webinar series, and I'll be focusing on specifically structural failure analysis. So dive right in, failure. Nobody likes this word, right? But it happens. And since it happens, we definitely want to try to prevent it. So we're looking at solutions to do failure preventions. But if you want to prevent something, you have to learn about it. You have to know the in and out of it. So before that, you have to do failure analysis. Well, and there are many types of different type of failures. And like I said, today we'll be focusing on structural failure analysis. So the first question comes to mind would definitely be, well, what is structural failure? Well, in fact, that is the first question that you should ask. And hopefully through today's webinar, you will learn first, what is structural failure? Secondly, what leads to structural failure? And thirdly, what are the signs of these potential structural failures that you can look for in your product or your materials? And lastly, how X-ray CT helps you navigate structural failure analysis. So the first question, what is structural failure? Instead of giving you a bunch of definitions, I feel like it's always good to use examples so that you will have a more vivid mental image, and also knowing what's the cause of structural failure. And the cause of structural failure can be very devastating. It can be catastrophic disaster. Like imagine you see a picture of the airplane on the left. You probably don't want it to experience structural failure when it's during mid-flight, but unfortunately it does happen. Here you can see that's what happens if you have structural failure for a plane, and some examples. What you're seeing here in the center is a picture of an airplane, the Comet 1. It's an airplane from the early ages of the aviation history. In fact, I believe this one is actually the first ever commercial airliner. And what happened to it was it experienced a structural failure during mid-flight. And you can see it's all the remains that we could recover broken into pieces and falling down to the ground. Well, structural failure can be catastrophic, not only to the engineered models that we're seeing here, like an airplane. It can also be devastating when it happens to something that's immobile. Imagine like in a building, and if the building suffers structural failure, well, it can also still cause a lot of human lives. And it's not something that happens rarely. Just a simple search on the internet, you can see a lot of information or news articles talking about this information, this kind of events. Like here, an example from UK, people were concerned about the concrete that's being used in the buildings that might cause structural failure. On the other side of the globe, in Australia, there's also similar concerns of the materials that's been used in these type of usage case, like building structures. Now, not all causes of structural failure will cost human lives. Well, that's definitely a potential. But even when it's not causing lives, it can still cause a lot of human pains. Like if you have a failing product, in this case, like the picture on the left, from a artificial implant, artificial joint. If it's broken in half, even before putting it into the patient, it will be troublesome. But if it's broken after it's putting into the patient, well, you cause a lot of human suffering. And there are examples like that. Here, there are examples of artificial hip implants that broke after implant. And the cause of it is not only human pain, but also money, right? Your company will suffer a blow to their reputation. Here's an example reported by CBS News that Johnson & Johnson had to pay 120 million just to settle the lawsuit. Now, again, the last example here, actually, I would like to bring up is not as devastating. It's not causing human lives. It's not causing human pains, but it's still causing your reputation and possibly your revenue. Imagine you have a new phone as you just put on the market. Everyone was expecting it. We're so excited about it. But it turns out your monitor screen is very fragile. It's very prone to structural failure. Well, it might not be devastating to your product itself because it might still function, but it will be devastating to the reputation because there will be news articles talking about the most fragile smartphones that's on the market and how costly it is for your phones if you want to buy this type of product. And there might be even some influencers or YouTubers starting to make videos ranking the cell phones, and yours will be on the bottom of the list. Now, these are all very valid and vivid structural failure examples. So after going through these examples, I would like to ask you some questions regarding these samples. So I will hand it to Angela for our first polling question.
All right, thanks, Ted. So I'm going to launch our first poll question for today. Hopefully you should see this. And what we want to know is from you is what is the common cause of all of the structural failure examples that Ted showed you? Is the common cause fracture, thermal expansion, leakage, or corrosion? And Ted, we're getting lots of people answering, and it looks like there's a clear winner here. So for sure. So we're going to give everybody just a few more seconds. Yeah.
Yep.
We got over about 60% of the people answering, and definitely increasing. I'm going to give 3 more seconds. 3, 2, 1. I'm going to close this poll, and I'm going to share the results with you. And the leading winner here is fracture. So I'm going to send it back to you, Ted.
Okay. Thank you, Angela, and thank you everyone who answered all that, who all answered that poll question. And there's actually not like I saw a lot of answers for different options, and they're all very valid because a lot of times one can lead to another. But like most people are agreeing here, the common cause that we're seeing for all the examples I just brought up is fracture or something breaks, right, broken. So it is quite clear now fracture has very important roles to play in structural failure. In fact, all structural failure will have to experience fracture. Well, then the question is, what is fracture? You probably already have an idea in mind. You also definitely experience it in your daily lives. But to put it into words, what is the definition of fracture? Well, it is the separation of or fragmentation of a solid body into 2 or more parts under the action of stresses. In this case, the solid body we're talking about here is the structure. So the structure fractures, we have structural failure. Now, knowing fracture is so important, we should definitely take a closer look at what is fracture. What types of fracture are there? Well, there are several types. The first one is simple fracture. The second one is impact fracture. Third one being fatigue fracture. And lastly, environment-assisted fracture. Let's look at the simple fracture first. So what is a simple fracture? Like its name suggests, it's definitely the most simple, and you'll be right. Imagine a pen or pencil you're seeing here, and you try to bend on that pencil. Well, the pencil is not designed to be bended by you, so it breaks. So simple fracture is very straightforward. The force is too strong for the intended usage of that structure. For impact fracture, you definitely also have first-hand experience. Imagine you're trying to break an egg, you're trying to make an omelet. How do you break it? You probably don't hold it in the center of your palm and try to squeeze it, right? You knock it onto something sharp on a very specific spot, and it's broken. While you actually just induce impact fracture. Impact fracture is concentrated force in a short period of time on a very concentrated area. Now, moving on to fatigue fracture. Here you're seeing a soda can, and when you're trying to open the soda can, you pull on the tab, right? The tab is just bent and you open the can. Well, if you bend that tab a couple more times, you're actually not exerting more force, sometimes even less force, but you just do it more times, then eventually the tab will come off, right? This is fatigue fracture. It's not determined by the force only, but also it's determined by the great number of loading cycle that it experienced. And lastly, environment-assisted fracture. Some good examples include corrosion. Like you imagine a product that's functioning in salt water or very corrosive area. It will definitely be also attacked by the environment. Or in some other cases, it's operating at an elevated temperature. More use cases mostly talking about, let's just say, jet engine, the turbine blade. They're always operating at a very high temperature. And during high temperature, you can expect it's probably not going to behave at the same way during a room temperature. So these are high temperature failures, or more specifically, we call them creep. Now, these are different type of fractures, but all of them actually happens through a specific steps. So we want to know how fracture happens. How does fracture happen? Well, imagine here we have this is just a simple glove you can find in any lab. I cut a piece of it from the glove. You can see at the center, the picture. Now imagine you're using it in some ways. Maybe you're using it using too much force, or you just rub it against something sharp, and you may using it and keep using it, keep exerting more force onto it. That small damage will grow, right? So that small damage grows and grows further, and eventually it will lead to the rupture of your product or your material. It breaks into two pieces, the definition of fracture. And these four images actually are the process of fracture. They are damage accumulation, nucleation or formation of more cracks or voids, growth of cracks or voids, and lastly, rupture. And if you're already doing failure analysis on products, chances are you're looking at least one of these stages. You can be looking at all of them, but at least you're looking at one of them. So let's go through them one by one. First, the damage accumulation. The first role come to mind for failure analysis is definitely some field inspection roles, a lot of times surface level. And some examples like examining the brake. You pull your car into the mechanics to look at the brakes because you expect it to have surface damages. You expect damage to accumulate and you don't want it to fail, right? You don't want your brake to fail. So you want to examine it to make sure the damage is not too great to lead to the next stage of fracture. Or it can just only be you're expecting your product to be operating in a very harsh environment, and you just want to spot any damage at the first time, at the earliest convenience. The next stage is nucleation or formation of more cracks or voids. This is arguably the most popular stage of failure analysis because it is something that's happened inside of your product and can be formed not by damage sometimes. It can just be formed via processing. But if it's caused by damage, it is still something that field inspection will be looking into. In this case, it's more internal. Like in this picture, you're seeing someone using an ultrasonic device to look at the cracks and voids inside the railroad. And obviously, it'll be of interest to quality assurance to make sure the production process you subjected your product to didn't cause these voids or pores. And lastly, for R&D, you want to know what's a process you want to develop and what's a way to make your product better. So you want to look at this stage. The next stage, the growth or coalescence of cracks or voids. This stage is not as popular for failure analysis because it is already very, very close to fracture, to the rupture. But in some cases, maybe this is exactly what you want to learn. Because for examples, if you're doing mining or drilling, failure will actually lead you to what you're looking for. Or you're from academic or more research side, you just want to learn the process. You want to learn how exactly this kind of failure happens in certain type of materials or in certain type of ground or geographical settings. And lastly, the final stage is rupture. Obviously, if you're doing post-mortem analysis, this is the only thing you have left over. So if you have a foam that's broken, well, you don't know what happened. Now it's time to find out. You're looking at the ruptured or failed product, and you're trying to find the reason for it. So obviously, because of that, quality assurance R&D are coming into play again. They want to know, okay, this is the final result of failure. What can we learn? And also, arguably, this stage is the most familiar with everyone because you might not even know or notice the first three stages of fracture, but you will for sure notice your product is broken when it's shattered or broken in your hand, right? So These are the 4 stages of structural failure, or I should say 4 stages of fracture. Now, I think it's a good time to move on to a second polling question. So I will hand it over to Angela again.
All right, thanks, Ted. So I'm launching the poll question 2. This is the second and last question for you today. And the question is, which stage of fracture are you most interested in? So are you interested in damage accumulation, or instead are you interested in nucleation of cracks or voids? Are you interested instead in growth coalescence of cracks or voids? Or instead, are you interested in rupture? So those 4 different steps that Ted described.
And it's multiple choice.
Yes,
Yeah, you can select more than one.
More than one, that's correct. So you can answer 1, you can answer all 4. We're just interested to know what you're most interested in learning about. So it looks like we've got about 70% almost answer it. So I'm going to give a couple more seconds, and now I'm going to end the poll, and I'm going to share the results with all of you. So it looks like nucleation is of the biggest interest, followed by growth and coalescence, then rupture, and then finally damage accumulation. So I'll stop sharing this with everyone, and I'll send it back to you, Ted.
All right. Thank you, Angela, and thank you everyone again for answering the polling question. And yeah, you can actually see, like I kind of expected, voids and pores are very interested to a lot of people. But at the same time, we have a lot of interest in other aspects too. And it is natural because these 4 stages of fractures are all very informative. They can tell you different informations regarding fractures. So if we move on, so we know about the fracture, we know about the fracture stages and how important they are to failure analysis. Now we must ask questions like, okay, what do I see in my product that can tell me these failure or these fracture stages are happening, or there's a potential these fracture will happen, right? So how do you spot the fracture potential? Well, they manifest in your structure basically as structural weak points. And there are many of them, and some of them are very specific to certain type of materials or product, but there are ones that's kind of universal. Like if you see them, it's not going to be good in any of your product. The first of them is sharp angle. The second is cracks. And the third one is pores and voids. And lastly, I will still mention some others that's more pertaining to specific specific materials or specific use cases. Now, so the first, sharp angle. Why is sharp angle a structural weak point? You see here, this is a picture of the packaging of a protein bar. This is what I eat before going to gym every time before going to the gym. And on any packaging of the snacks, actually, you often notice these kind of jagged edges, right? And you probably immediately know, okay, if you want to open it, you tear it open from there. And why exactly is that? So, well, if we look at a schematic showing the sharp angle, well, in this case, it's a bit of an exaggeration. It's a bit deeper, but it's still a sharp angle. And when your product is operating or you're trying to actively open the package, you're exerting force, and there are stresses on your material, and expressed here in the terms of sigmas. And you can see in the material, you have these lines, and they are indication of how the stress or the load will travel in your material. So if away from the sharp angle, the load can just travel through your material just straightforward, just in a straight line, and be distributed evenly in your material. On the edge that's closer to the sharp angle, the force cannot travel through thin air. It has to travel through the material. So you see there is a concentration of load at the tip of the sharp angle. So your sharp angle will be expecting higher forces or higher stresses comparing to the actual stress you're exerting to the whole material. And that will try to tear that sharp angle further down into your product. And that's how you open your snack. So the same way that makes it easy to crack open the package is also going to make it easy to crack open your product. And you probably don't want that. Now, moving on to cracks. If we're talking about surface cracks, we can use the same picture here. It's basically just a very deep sharp angle at the surface. But sometimes cracks can be just internal. It's not on the surface. So if we rotate this image and just mirror it, well, now we have internal crack, and still with the load or stress distribution lines perfectly demonstrating the concentration of forces at the tip. And if we show it on the right, it's actually a similar demonstration, but in this case, we even add in the dimension of the crack that we're seeing with the longer edge, longer dimension to be A or 2A, and the width of it to be B. Now we know there's a stress concentration on the tip, but how much exactly? So we know it's going to be larger than the sigma that you're experiencing, so we can just call it sigma max at the tip of your crack. There's actually a very useful term or theory to describe how large this sigma will be in relation to the force you're exerting to the whole product. Well, I assure you, this is the only equation you'll go through this webinar. I know like math can be kind of confusing, but this is a rewarding one. So, and this is the only one. So this is called the Griffith model. It is expressing what is the sigma max you can experience or you can expect in relation to the sigma, the overall force you put on your product, and the dimension of that crack, so A over B. So just from this simple term, you can expect, oh, if my crack is very narrow and long, that A over B term will be really large, and then we're expecting a larger sigma max, right? Now, let's just say if my crack is not narrow and long, then what happens? Well, you're basically looking at a pore. So if we assume a perfect pore, a perfect sphere, now the dimension of A is the same as B. 2A is actually 2B now. Does that mean I don't have to worry about it? I don't have sharp angles anymore, right? We look at the Griffith model again. Now A over B is basically 1, right? It's the same length. You are still looking at 3 times at least the force that you're putting on your product at the edge of your pores or voids. So simply by existing, pores and voids will be a structural weak point. And what's more, pores and voids usually don't happen individually. They usually happen in close vicinities with each other. Like in this case, it's another real life example of pores that's been used as an easier way to open an envelope. It even has an indication saying, oh, tear at the perforation. So when you have multiple pores near each other, they will lead to the connection of each other. And because of the heightened strength, they will break open and connect with each other and finally become a crack and rupture your product. So now you can see how pores, voids, cracks, sharp angles is a structural weak point that you don't want in your product. Now, moving on to some other structural weak points. Some of them, like I mentioned, is more specific to the type of material or type of product that you're having, but a lot of times they still lead to the same concept. What do I mean? So let's look at some structural specific flaws. Sometimes you have inclusions or you have fibers like a carbon reinforced fiber composite, right? For inclusions, if you have mismatch between your inclusions and your matrix, well, then the edge will tear open. Then you essentially still is creating a crack or a void in your material. Similarly to fiber mismatch, if you have random breakage of your fiber, well, you're creating voids and cracks inside your product. So although it's not technically exactly the same, it leads to the same idea why they are structural weak points. And the next one is not exactly the same, but it's also easy to understand, is if you experience a reduction of load area. And it can happen to materials that are more ductile when they're necking, or it's just simply caused by a manufacturing error. You expect an area to be thicker, but actually not as thick. So what is necking? This picture is very perfect summarizing what is necking. So if you have a product looking like this, you have a reduction of a certain area. Imagine the load lines or stress distribution we saw earlier when we were explaining the forces. You can expect the thin, narrow area is going to experience a lot of the loads, right? And it's probably going to break at that point. And because it's thinner, it looks like a neck. So it's called necking. Now, finally, we have some environment specific flaws, and it can still tie back into a lot of things that we learn. Let's just say we mentioned about in corrosive environment. If you're in a corrosive environment, maybe on the surface we'll have some corrosion pits or corrosion layers that's having sharp angles. That's basically leading back to the stress concentration concept we talk about all this time. Now that we know about, okay, what to look for in our product for structural failure analysis, what are the methods people use for structural failure analysis? Now, when you're trying to do structural failure analysis, there are many methods. Before you want to even look at your product, maybe you want to do some standard testing. Like, I know what my product is made out of. Let's make standard testing samples and test it under the expected condition. Then I'll know if it's going to fail or not, right? Well, for some cases, that's good enough. For a lot of cases, especially if your product is more complex or more intricate, or the operation condition is not as simple, you probably cannot have all the answers using just that. And nowadays, we can use simulations to help that, using simulations to factor in those different aspects of operation conditions. But still, at the end of the day, you have to ask the questions. Are these actually the same as the behavior of my product, right? So in the end, you have to be grounded in reality. You have to still look at your actual product. So actual product inspection is always going to be there. So how do we do that? Well, microscopy. People use microscopy all the time, and they're very useful, either optical or electronic, like scanning electron microscopy, SEM. Or ultrasonic fault detection. We just saw it briefly when we were talking about damage accumulation, right? It is a way to look at the internal structure. Well, actually not look at. It tells you if there's a crack or void of certain size, but you actually can't see it. But it still can be useful information. And X-ray radiography. This is the first step trying to look inside of a product, but it's still 2D and everything is superimposed together. So it can be ambiguous sometimes. And lastly, obviously, in my opinion, the most useful one, the X-ray CT, which gives you a full view of internal structures undestructively. Now, with all these tools, why would you choose X-ray CT, right? If we look at the tools for structural failure analysis, we know we're looking at those structural defects, pores, cracks, all those kind of things. They're probably staying within the range of this scale. They're not likely going to be the size of virus. You're not looking at atomic level. If you're looking at those, you're more into material choice or material science rather than structural failure. And they're not likely to be as big for your plain eyes to be able to see. But even within this range, you have multiple tools, X-ray microscopy being one of them, but you still have optical, electronic microscope. Why would you choose X-ray CT? Well, we can actually use the different stages that's also relating to the interest you have when you're doing failure analysis to help us identify why CT is very advantageous. So first, non-destructive and destructive separation. We know SEM is destructive because you have to section your sample. It's very limited sample size you can put into the vacuum chamber, but it is very useful, give you a lot of information for nucleation and crack growth inside, because you can see inside all those 2D, and the growth of cracks and voids and even fracture, rupture state, doing some like photography. You probably don't want to do damage accumulation tests using SEM because you need to cut your sample. If you're just looking for damage inspection, you probably don't want to use destructive techniques. But for that, you still have many of the non-destructive techniques, including X-ray CT. X-ray CT arguably can give you all the information because it creates a digital twin of your product in the digital space for you to manipulate. But why would you choose that other than using both optical and X-ray radiography, since they're all non-destructive, right? Now, the data you're acquiring that inherently they are 2D or 3D is very important, because no matter how many 2D images you take and use how many quantification or statistical estimations, you're always only looking at one single surface. You always have to ask yourself, am I having some sampling bias? Am I just looking at a very specific cross-section that's not showing me the whole picture? So in this case, 3D techniques are having an advantage. In X-ray CT and ultrasonic examination, both give you 3D information, right? Then why would you choose X-ray CT other than ultrasonic examination? Well, because the type of 3D data you're obtaining through the technique also matters. So let's just say you know there's a crack in there in your product using ultrasonic examination. It is very different that if the crack is at the insignificant edge or corner of your product that's never going to experience any load, comparing to the same crack but at the dead center of where the load is supposed to go, right? You want to see where they are. And ultrasonic examination cannot really do that as effectively. Well, X-ray CT can, it lets you see it directly. Well, with this, these are categorization of all these techniques. How about some actual examples? I'm playing X-ray CT can give you all these good structural information. Let's look at some examples of what kind of structural information X-ray CT can provide you. Now here you're looking at is a grain of sand. You can see the scale bar there is quite small, right? But what's so special about this sand is actually its origin. It's not on the Earth. It's from the moon. It's from Sea of Tranquility. Actually came back from the same mission that humanity first ever step on the moon. It's from the same mission collected from Apollo 11. And that is already a good enough incentive to not use destructive techniques right off the bat, right? So with X-ray CT, this is what we get. We have a full scan of the whole grain of sand, and you can already examine it and tweaking the contrast to focus on different aspects inside. Like, oh, maybe I'm more interested in the higher density particles inside. Now I can just look at them using the adjustment of contrast. And since you have a digital twin of your whole sample, you still have the freedom to slice through it and in 2D, because a lot of times 2D inspections can still be very informative. And with the 3D data at your hand, you can do that however you want, wherever you want, whichever angle you want. And by the way, this is a paper that I just published a couple months ago, working with my good colleague Ishan and Hamid under the supervision of my advisor, Professor Chola and Professor Thompson. It's open source. I encourage you to check it out. Now, here, this is a 2D sliced image of that CT scan. So it's analogous to what you're going to expect when you're doing the SEM image. But the difference is you don't have to cut it open. And I can do how many times this kind of 2D size I want. Well, it's not exactly the same kind of resolution you can expect from SEM because SEM is still a very powerful tool. But the good thing about CT is you can use CT to get a good view and decide which cross-section you want to look at using SEM. And after you exhaust all the information you can get, because here you can still, I can spot a lot of the key information inside the structure still using just 2D CT without SEM. But if you still need information that CT cannot provide you readily, well, you can do that. Then you just do SEM analysis like I did here. I want to know the composition. I want to identify the faces inside. So I did EDS on the SEM sample. And what do I know now? Now I know what faces there are, and I can relay those information back into 3D using X-ray CT. And because of that, what I get is I have a full grasp of what different faces are distributing inside the particle in 3D. These are the pores that we're looking at and how they distribute. And these are the higher density particles and what their compositions are and how they distribute. And also some of the mineral class inside. Imagine this is your product and you have different areas you're interested in to see if they have pores or cracks. Now you know, and even know about the composition because CT is also a very good tool or centerpiece for you to correlate a lot of information back to, elevate it into 3D. And before we dive into the next section, I feel like it's probably a good time we stop for some Q&A.
All right, thanks, Ted. So one of the questions came in very early, and it was, is surface inspection alone the only detection method for the damage accumulation stage? But I think you answered that on slide 37. If you want to reiterate that, so again, this is surface inspection for at the damage accumulation stage. So I think you have optical and obviously CT, or you know.
So you're actually perfectly right. So when I try to separate different stages and correlate it to different aspects of failure analysis, because damage accumulation, they all happens in chains. So damage accumulation leads to the nucleation and growth of those cracks and pores. So a lot of times they can blend into each other. So when you're still doing damage accumulation, sometimes the damage can be internal. It can be just the growth of your internal cracks and pores. So yes, even for damage accumulation, it's not limited to just the surface. You can also do that for the internal structures. Yes.
Okay. One more question, actually. This is excellent. How did you match your SEM image to the CT image? How were you able to map, what you got on your SEM side to the actual CT?
That's a very good question. So if we look at this image, I think you can actually see. So obviously, for very, very tiny particles that's outside of the resolution, I wouldn't be able to tell, right? Because the CT, it gives you a very good representation of the internal structure, but it still has everything has its limit. But because CT in this case has its contrast based on the density and composition differences, so we're already seeing some contrast. And on the right side, this is an SE image and specifically an EBSD backscatter electron image. So we know backscatter electron image also gives you a contrast. The darkened area and brighter area you're seeing here is also correlating to their composition and their elements. And with that contrast, I can identify the particles or the minerals here inside. And because if they are the same material, they will have the same, or if they're the same phase, they will have the same contrast throughout your CT scan. So because of that, I will be able to correlate back the information I get from SEM and look at this type of contrast inside the CT and identify them as the phase I was looking at in SEM. So that's how I correlate the information back into the CT using the contrast differences. And yes, it will be challenging if everything you're looking at is having very, very minimum contrast.
Okay. All right. Thank you. We'll answer a few more questions at the end.
Okay. Thank you so much. So now let's move on to the next section. So that example of lunar dust is, I believe, is very informative of the capability of CT, but that is not exactly failure analysis, was it? I wasn't doing failure analysis on lunar dust. So how about some examples of actual samples that we're looking for structural weak points and the defects that we talk about using CT? So let's go into the structural failure analysis X-ray CT examples. So the first example is a 3D printed structure that I made. And on the left picture here, this is one of our equipment, the Ski Lab HX, with a sample in the center here. You can see a zoom in view on the right. And this is a cone beam X-ray source. Well, the detector is out of view on the right side. So the product here, the 3D printed structure here is 2 blocks on either side of 5 cylindrical pillars. So what would we see when we turn on the X-ray? Now, this is what you see, or what the detector sees when you turn on the X-ray. There's a single one angle 2D radiograph. And even with this, you're already seeing, okay, there's something happening in the center pillar here. There seems to be different contrasts. Maybe there's a pore, there's a gap in there. Well, if you're willing to do X-ray CT, just doing the X-ray radiograph or scans from all 360-degree angles, we will be able to reconstruct it into a 3D. So by 3D reconstruction, we will have the 3D model. Then if we have the 3D model, a digital clone of our product, we can just slice through it and look at the inside and find out what's happening. And that's exactly what I did here. So you can see here, and we immediately see, okay, there's definitely something happened in there, and it's not as simple as just a gap. And let me highlight those pores and cracks for you. So we can definitely see cracks and pores happening, and something of a different phase, of a different contrast. So what exactly is happening here? So if we look at a 2D cross-section of the 3D model here, this is what we see. And if we zoom in at the center area, because I know the process of this 3D printing, so immediately I can tell, those darker areas are actually the wax. They were there supposedly acting as a temporary support for the printed material. And after the printing, they're supposed to be leaked out. But I made a mistake here. You can see there's supposed to be like an extension of the gray, darker gray phase all the way to the end, but I didn't leave a hole for them to leak out. So they got trapped inside. I didn't expect it. And since they got trapped inside, and the wax and the material we use to print definitely has different thermal expansion. So when it cools down, the wax contract and form all those pores and cracks. And that contraction also gives force, right? The different contraction between materials give force. And that actually leads to the crack growing into the actual material, the actual 3D printed structure. I wasn't expecting that. I designed the vacancies inside, but I didn't expect the wax to be trapped inside. I didn't expect there's a crack actually growing into the 3D printed structure. So kind of in an accident, this is the perfect example of a failure defect that's there that I didn't expect, didn't know about, and only found out because I did an X-ray CT scan. And the whole 3D printed structure is still fine. I didn't cut it open. I just do a CT scan. I found out this information. And that's not all, because that's already very informative. But since we have the image of the cross-section of the internal structure, now, like I mentioned, it's all based on contrast, right? X-ray CT. So contrast means a different distribution of brighter or darker grayscale. So for the whole picture, we have a distribution as grayscale histogram. Now, they correspond to different areas. Like here, the brighter peak on the right is most likely the material that we use to print. And the darker peak on the left is the pores. So I can say, hey, let's just select the darker area inside of this structure. And then we have the pores and cracks highlighted, right? And we have the 3D data. So why not just do that to the whole volume? And if we do that, we will be able to highlight and just circle in a way where those cracks and pores are in a 3D space. And this is exactly what you see here. And not to mention, this is already a very good 3D visualization to tell you where exactly the defects you're going to be concerned about are. We can also do quantification to these aspects. So we know that, okay, if we have a very large pores or cracks, that's definitely a bad thing to have. But what about the smaller ones? What about the smaller pores? Are they going to be a problem? Remember, we talked about Griffith's model, right? So the sharpness, the dimension of those smaller pores and cracks are going to be detrimental. So why not just look at the dimension of them? So in this Griffith model, remember the A over B, that's the dimension of your crack or voids, but they're basically aspect ratio. So I just ran an aspect ratio analysis on the smaller pores, and I will have a distribution color-coded and also in non-numerical definition if they're going to be bad for our product or they are negligible. And by the way, these information, the process of the and renders so far you're seeing are made using a software called Dragonfly, which is a very powerful tool for a lot of 3D analysis. And 2D analysis, you can definitely use it for SEM too. And now this is not the only thing you can do with CT data, because once you have a digital twin or digital clone of your product, printed using the 3D printed CAD model, are you sure it's the same? Because if you're more familiar with 3D printing, it's a very tricky process. It can be your unevenness of your nozzle, like a protrusion, or if you're using metal printing, what's uneven melting of your laser melt pool, all those kind of things can cause different anomalies. So wouldn't it be nice to see if our actual product match the CAD model? So you can do an overlap and do a nominal to actual comparison. In this case, we can immediately see, okay, there's something going on here. The red indicates thicker than the intended dimension, and the blue indicates thinner. So immediately we know one pillar is too thick, the other pillar is too thin. And if we have a 2D cross-section view, it's even more clear. The red is thicker and the blue is how thin it is comparing to what it's supposed to be. So in this case, imagine if it's a load-bearing product, it might buckle, right? Because you have uneven loading, then you have uneven thickness of your load bearing pillars. And by the way, this result, like the nominal to actual comparison, is done using the software called VG Studio, which has a fantastic surface definition. That's how we did all these nominal to actual comparison. Now, maybe you're thinking, okay, this is all nice and well, but this is still quite a big product, right? You're using millimeter here. What about my product if it's smaller? If you're X-ray microscopy, what's the capability of looking at smaller areas, smaller details? So the next example is the CFRP, carbon fiber reinforced polymer. So again, we're looking at 2D radiography. You look at scale bar, this is now at the micron level. And during the scan, you have radiograph from all angles. You can definitely see different fibers going different directions, different bundles of fibers, but it's probably not informative enough just with 2D radiograph unless you have a super huge flaw, right? So if we do X-ray CT for, let's say, a smaller area, then we can immediately see, oh, if there is any crack in between, there are laminations happening for my fibers, and well, look at that. You have a crack in between your fibers and your polymers. There's definitely some laminations happening. And if you do a 2D cross-section view, this is something you will probably see if you are to do a 2D SEM. With SEM, you have higher resolution, sure, and you can do similar analysis like a 2D measurements I did on the right, but you will never be able to tell how deep the cracks are going into the fibers and how devastating or how connected this crack network might be, right? So using X-ray CT, you can have the answer of that question by doing segmentation. Now, and there are times when if we want to do a similar process we did earlier, just selecting the darker area or the darker area of the picture, then we highlight the cracks, right? Well, but sometimes it will turn out like this. This is a case of you don't really have a lot of very sharp contrast for a lot of faces. Then it'll be a headache to do analysis, right? But the good thing about CT that putting a digital clone in the digital space is that you also have the whole arsenal of tools that's available in the digital space. Like now it's all the rage of talking about AI or just algorithm or machine learning. If I just painted the areas I, as a human, can tell is the fiber, polymers, and cracks, and leave it for the computer to do the hard work for me, to do training, manually inputting this limited training data and let the deep learning do the work, I will be able to let the PC to do the segmentation for me. And now I have all the different faces I was looking for individually labeled. So with that individually labeled, you can separate them and do all the analysis you want. In this case, for the cracks, remember the Griffith model. Now you can analyze if they are too sharp, if they are too large at a specific area you don't want. Or maybe in this case, you are more interested in the fibers. You want to know if your fibers are continuous, if they are broken into smaller sections or pieces. Well, then might as well run a volume analysis of the fibers. In this case, again, you have visualization of how the fiber distribute, what's your volume distribution, and quantification. All these are possible with CT, and I didn't cut the sample. This cube you're seeing here is just a digital crop out. My sample is still sitting on the sample stage. I didn't cut it. Now, the last sample example for the day, this is a car, a sports car, but it's not an actual car. It's a 3D printed car again, but this time it's a metal printing. It's a super alloy. It's an Inconel, actually, a very popular, common super alloy. And you can see the grid-like structures in it. It's very typical for a lot of 3D printing structures. And I can definitely do something like thickness analysis here to look at different thickness distribution of the grid structure to give me an idea of, okay, if it is to subject to load, maybe the thinner area will buckle, maybe the thinner area will be too thin. But there are times you'll be like, Ted, that is not enough. I look at it and I see, okay, somewhere is thicker, somewhere is thinner, but I don't know if that's going to be damaging to my product. I would like to do some simulation. Well, can I do that? Well, you definitely can, because again, creating a digital clone enables you and opens the doors of all those operations. Let's just do some simple load distribution simulation here. Here again, this is a mesh that I created using VG Studio of the same scan. And with the mesh created, I am going to be able to do some load distribution analysis. In this case, let's imagine we load the car from the top, from the ceiling. Let's push against it using like 150,000 Newton. And now you have the distribution of max principal stress. You can also do volmesis if you want. In this case, the red indicates a lot of tension, and the blue and purple means mostly compression. And again, you can slice it open since you have the whole volume at your disposal. So you can look at, oh, okay, the intersection of the grid-like structures and how it distributes. There are areas around the wheels that's experiencing a lot of tension. Maybe I want to modify the printing to make it thicker there or things like that. Or you're just only concerned about compression. And it looks like compression is actually distributed quite well. You don't have to worry about it. And you also have the freedom to look at it in 2D to give you information from different angles, or to just give you more idea of how to optimize your product. And this is also just done in VG Studio, and you can definitely port your scan into more dedicated simulation product for finite element simulation, like Abacus or something like that. So with all these examples finished, hopefully after today's webinar, you have learned what is structural failure. Well, it's caused by fracture. We know fractures happen when you have a structural failure. What leads to structural failure? Well, fracture leads to it, and we learn about what type of fractures are there and what are the steps of the fractures and how they correlate to the process of failure analysis. And what are the signs of potential failures? They're basically talking about the structural weak points, the defect, pores, sharp angles, cracks inside your product that you want to look out for. And finally, how X-ray CT helps you navigate through structural failure by providing you the most comprehensive 3D data of your structure that you can still correlate with other techniques if you really need all those information and elevate them into 3D. Now, thanks for listening, and let's head in our final Q&A session for the day.
All right, thanks, Ted. Really interesting session, and thanks again for presenting. So we do have time for a short Q&A. I know we're approaching the 1 hour mark here. So we had some really good questions come in. The first one, actually, the asker said you already answered them, but I wanted to make sure that I read aloud so that you can also respond. So on the moon sample, right? So obviously it was difficult to segment the phases that are so similar in the grayscale. And he said, so how do you clearly segment those different phases? Was it machine learning, and then what software were you using for your material?
Mm-hmm. Yeah, so you made a really good point. So for moon samples, and not actually just moon samples, because I also worked on meteorites, and I know a lot of minerals are having very painfully close contrast. So yes, a lot of times it's painful, manual, and some machine learning. At the time when I was a PhD, I didn't have access to all the machine learning, but I did have some extent. And for CT, because again, contrast comes from your CT. So you're not limited to only just use one CT scan. You can scan it using different energy ranges to highlight different contrasts of different phases, and then put them together into your final data. So that's what I did. I did multiple scans, focusing on different phases, and yes, a lot of painful manual segmentation, but I think it's quite rewarding. Yeah, and for the software, so a lot of the segmentation I showed today are done by Dragonfly. At the time when I was doing that segmentation for my PhD, I was using Aviso, but they're all equally very powerful tool and having a lot of different ways for you to do segmentation.
All right, thank you. So again, going back to your lunar sample, from the comparison of your CT-SEM images, could you use that machine learning to work on a larger area, or did you actually? I assume you likely did look at the entire, right? Even though it was only this big, right?
You
from
definitely,
the small SEM,
yeah,
right? You expand that to the entire sample.
Yeah, you definitely can. And I wish, I mean, it's also like an advancement of technology, especially since the AI algorithm is having a huge leaps recently. And it wasn't the luxury I had when I was doing the research. So I wasn't able to do a large scale machine learning at the time. But yes, it's definitely possible. And I would say it's probably the more preferable way for more complex samples, because a lot of times it also offers you a more subjective segmentation process comparing to manual, because like you come in today or tomorrow, or you're having 1 or 2 more cups of coffee every day, your segmentation process might vary a bit. But for machine learning, they are more consistent. So yeah, you can definitely do that.
Okay. All right. Couple of more questions. So the next one here, I believe this one came in during your 3D printed like pillar. Is, could you consider the shape of the voids, like sharp edges with higher stress, on the large and small pores? And then is it possible to quantify? And I can read that again if you didn't catch it.
Yeah, so you can definitely look at the shapes. Like I kind of did some aspect ratio analysis, but there are a lot of tools like fair diameter, sphericity, or just a bunch of different quantification methods for you to define the shape of your particle, in this case, the voids. And once knowing the shape, you can do a lot of categorization and calculation to estimate their stress concentration. And just kind of like from my experience, not exactly doing the same thing. I had a colleague, again, back from the same lab, Professor Chala's lab. He was doing quantification of different particles of 3D printing metal like powders. And the powder's geometry will affect how they agglomerate together when they're being molten. So in this case, for you might want to do the same shape analysis and then do stress concentration analysis instead.
Okay. Okay, thank you. I think this will be the last question we ask, and this is actually a pretty broad question. So go with what you feel is correct. So what's the spatial resolution for CT, right? I think you saw the question come in. What's the spatial resolution? Of course, it depends.
So that's a really good question. And in a way, yes, it's a variable, but there's still a ballpark. And just kind of like SEM, when you have super high resolution or even TEM, you have more limited field of view. And it's kind of similar to CT. There are some variations, but the highest resolution you can aim for, you have submicron. You have, I would say, maybe 500 nanometers, or sometimes even pushing further, but I would say submicron around 500 nanometers spatial resolution is what we're looking at for the more high-end accessible lab scale equipments you can have. But those kind of equipment, you also have very limited FOV to a couple millimeters actually. But for larger samples, you're looking at a coarser resolution. But you can always do like a broad scan and then do a more zoom in scan for a more interested area for higher resolution.
Okay. All right. So we're gonna wrap up here, and that's all we have time for. There's still a couple of questions, and we will respond to those. We'll respond to those after our session today. Right. So be sure to join us next month for the third and final session in the series with Angela discussing structural failure analysis, functional structural failure analysis.
Yeah, functional.
That. Functional. And there is a link to the to registration page in the chat. Thank you for joining us, and we will see you next time. Have a great day.
Thank you, everyone. Thank you so much.
Bye, everyone. Thanks
Thank
for
you.
joining.
Bye-bye.